Hi, this is Scott Wilkinson, host of Home Theater Geeks. In episode 281, I chat with Jack Ockley-Brown, head of acoustics at KEF, about speaker acoustics and design. So stay tuned.
Netcasts you love.
From people you trust.
This is Twit.
Bandwidth for Home Theater Geeks is provided by CacheFly at CACHEFLY.com.
This is Home Theater Geeks with Scott Wilkinson, recorded November 12th, 2015. Episode 281, Speaker Acoustics with KEF. This episode of Home Theater Geeks is brought to you by Epson's new EcoTank printers. With Epson's line of SuperTank all-in-one printers, you can print thousands of documents without running out of ink. EcoTank is loaded and ready to print when you are. Visit epson.com/ecotank to find out more. And by Drobo, a family of safe and expandable, yet simple-to-use storage arrays. Drobos are designed to protect your important data forever. Visit drobo.com/twit and use the code TWIT100 to save $100 off a Drobo Mini, Drobo 4-Bay, or Drobo 5N. Hey there, Scott Wilkinson here, the Home Theater Geek and editor of avsforum.com. This week's guest geek is Jack Ockley-Brown, the head of acoustics at KEF, the makers of some really wonderful speakers. Hey, Jack, welcome to the show.
Hi, Scott. Thanks very much.
Oh, thank you for being here. Those of you who are tuned in live at live.twit.tv or logged into the chat room there or at irc.twit.tv can post questions for Jack as we go, and I'll pass along as many as I can. It always helps if you put my screen name in your message, which is my name, Scott Wilkinson, no dots or dashes. You can typically type a few letters and hit tab, and it should populate. But that way it comes up in a different color on my screen, and I'm able to see it a little better. So, Jack, tell us, let's start with a little bit of your background and how you came to be the head of acoustics at KEF.
Well, I studied acoustical engineering in Southampton at the university there. They have a department that's called the Institute of Sound and Vibration Research. And I went into that when I was about 17, 18, with the sole purpose of finding out how to design loudspeakers. I was already crazy into it at that point. I designed my first pair of loudspeakers when I was about 16, another pair when I was 17 in the summer holidays. So as part of the course, it's generally encouraged that you do some time in industry in the summer holidays, some placements. And typically people go off and they do acoustic consultancy, or they work in automotive industry and things like that. But I was determined to find some experience in the loudspeaker industry. So I wrote a letter and I sent it to every loudspeaker manufacturer that I could find in the UK. And I got one reply, which was KEF. So 2002, I worked for KEF for my summer holidays. And then they must have thought I was okay because they invited me back in 2003. And then when I graduated in 2004, they hired me as a research engineer. And I've been there ever since.
Wow.
So, it's now 2015, so that's 11 years later, and I'm head of research, head of acoustics, I should say.
That's
I'm
incredible.
Taking someone else's job.
So that was like your first job out of college, and that's where you stayed.
Yes, yeah. Well, I mean, I guess for me, when I got the job in 2004, it was just really suited me well, and it really kind of. I never reached the point where I felt I was stagnating. I was always kind of being allowed to push myself, and it's just been a really good experience for me. Working with a really good team, so I'm still here.
And you're filling some pretty big shoes. I mean, Laurie Fincham was there, Andrew Jones was there, working in similar areas to you. I mean, the lineage that you're following is quite august, shall we say?
Yeah, there's some pressure there. You're right.
Yeah. Well, and KEF is responsible for quite a few innovations that I really want to talk about today. Perhaps the most well-known is the concept of the coincident or coaxial driver, which KEF calls UniQ. Tell us how that came about and what's important about it.
Well, that was, I mean, you mentioned Laurie already, and that was something that really came to its initial stages when he was at KEF. I mean, there are other coincident units around that you'll see, but the thing that makes the UniQ unique is that the tweeter is directly in the apex of the cone driver. So it's right there in the middle of the cone driver. It's not behind, or it's not in front on a stalk. And this idea came about through a research collaboration that KEF were doing, which was called the Eureka Project. And it was looking into how listeners perceive sound in rooms and what a loudspeaker should do in order to maximize the quality of the audio in a normal room. And the outcome of the research all came down to having a really nice directivity of the loudspeaker. And that's what the UniQ achieves, and that's how it came to be because of this new knowledge from this research project. So I'm sorry. Very simply.
Yeah, go ahead.
I was going to say what you have with most loudspeakers, and indeed KEF's loudspeakers before the UniQ, was you have to have multiple drivers. You can't design one driver that will cover the whole bandwidth really effectively, and that's because you need a big driver at low frequencies to move a lot of air to make enough bass. But if you have a big driver, it's hard to control the vibration at high frequencies. And it's also very hard to control the directivity at high frequencies. So that's why, almost ubiquitously, you'll see multi-way loudspeakers if they're high quality. But the problem is, once you split up the sound into bass and mid and treble, you have to rely on the air, the acoustics, to sum it back together. And the trouble, if you have different positions for your different drivers, is that it sums up differently in different directions. Because the path length, if you imagine you're moving around the loudspeaker, the path length between you and each driver can change. So the UniQ, the idea there is you put the two drivers, the tweeter and the mid, or in some cases for us, the tweeter and the mid bass. You try and put them so that they're radiating as close as we can from the same point in space. And then once you do that, you end up with a situation where when you move around or you move your measurement microphone around, both drivers change at the same rate. And
well, sorry,
I was going to just add on the end to that, the little extra bit, which is a bit more subtle, is that you can use the shape of the cone of the UniQ, so the cone of the mid-bass driver, to control the directivity of the tweeter. So you can also match up directivity as well as the position.
Yeah, I was going to ask you about directivity, and in particular as it relates to frequency, because as we know, the higher the frequency, the more direct the sound is, the more directive, the more directional, I should say, the sound is. So I was wondering, how do you match up the frequency directivity with two different drivers in the same place? I would think that the cone, the mid-bass driver within the UniQ, would naturally be more dispersive than the tweeter. Is that not true?
It's actually the other way around. The directivity depends on the size of the source. So if you take a set driver size, and if you imagine you had a perfect driver that didn't break up at all, then it becomes narrow, and the point where the directivity starts to narrow is related to its size. So a small driver narrows at high frequencies, medium-sized driver narrows at mid, and so on. So
I see.
when you normally the problem is you have a small tweeter. So at around about 2 kilohertz, or wherever you're crossing over, you're going from something which is maybe 5 inches down to something which is maybe an inch or an inch and a half. And the directivity is wider on the tweeter than the mid-range driver. So you really want to try and narrow the bottom end of that tweeter to match up with the mid-range driver. And that's what we can do by using the cone to control the directivity in the UniQ.
I guess the cone is acting more or less as a waveguide for the tweeter, right?
Exactly. Yeah, that's exactly what it's doing. Okay. We spend a lot of time trying to get the best possible match. So optimizing, the size of the cone and then the shape of the cone. to control, the directivity of the cone itself, and then of how the cone's controlling the tweeter to get them to match.
Yeah. We have a picture of the UniQ driver from the Refprint series, which we're going to talk about a little later, that speaker. But but there's a picture here, and I just want you to quickly go through it. Obviously, there's a ton of components. There always are.
Yeah, there's a lot of stuff there. But if you start at the very left-hand edge of that picture, the first component you see is what we call the tangerine waveguide, and that sits directly on top of the dome, which is slightly to the right of that. And you've then got the rest of the parts that make up the high-frequency unit. So there's some magnets in there, some steel parts that carry the magnetic field. And then that all sits inside of the mid-range cone, which you can see more or less in the middle of the picture. And then as we kind of follow to the right, we're looking at the chassis that holds it all together, and then the motor system for the mid-range.
Mm-hmm. It's amazing to me that a concentric driver like this, or coincident driver, can have two different motor structures. They can vibrate independently, and yet they're linked together somehow. That always fascinated me.
So the aim is that the two motors don't move at all. So we clamp them together. They're held onto the chassis, and then we bolt them into the baffle, or in some cases we actually brace the back as well. Yeah,
I guess I meant the voice coil, or the thing that drives the diaphragm. That's going to move.
Yeah, so obviously they do receive independent signals, and you can get them to vibrate and move really quite independently without affecting each other, even though they're in that close proximity. What we do tend to do is use a three-way system design on our higher-end products because we can minimize the interaction that way. But even on a two-way loudspeaker where you're asking the cone driver to move a lot of air, the interaction is surprisingly low and doesn't affect the performance too much.
Now, KEF has made some really beautiful speakers. Some of them, as we talked about offline, are what could be called statement products, or similar to concept cars at car shows. And the one that I remember from several years ago that I just want to show the picture of because it's so beautiful is the Muon. This thing is really amazing. You might have been there when they put this together. Here they are with, I guess, the industrial designer, the guy who designed the cabinet, right?
The designer is Ross Lovegrove, and that is he in the picture there.
And these speakers are taller than he is.
Yeah, and he's not. He's a tall guy as well. He's taller than I am by a long way.
Wow.
Maybe that says more about me than him.
Well. What it says is that these speakers are gigantic and beautiful. I mean, the cabinets are out of aluminum, shiny aluminum. They're really beautiful.
It was quite a challenge to come up with a manufacturing method for that cabinet. The actual Muon was launched in, I think it was 2006 or 2007. So I'd been at KEF for a couple of years at that point. And I did a little bit of work on the UniQ. But it was really a speaker designed by one of my colleagues, Andrew Watson. And it, again, similar, we talked about this a little bit offline, but it began life as a kind of skunkworks project, something we were working on in the R&D lab in Maidstone in the UK. And we actually developed a pair of prototypes, which we called Austin, which was kind of code name, and we kind of give things code names so that you can talk about them fairly freely and not worry about who overhears them. And Austin was short for Austin Powers because it was a popular film at the time. It was a powerful speaker. And
okay.
The first ones we made were made from, knocked up in our I shouldn't say knocked up, carefully made by our technicians.
Thank you. Yes, very good.
They didn't look as beautiful as the final thing, but they sounded great. We took them actually to the Munich high-end show, but because they didn't look as nice as the final ones, we covered them in acoustically transparent cloth and just played them to people and said, "What do you think of this?" It was great. It was a great idea.
That's funny. Creamy Corncob in the chat room has put in a link to these particular speakers. So what makes them special? I mean, other than the fact they look so great, I mean, how do they sound really great? What is it about them that gives them a great sound quality?
With the Muon, I think the thing that is really quite unique is that they really are full range. I mean, you can see how big the cabinet is there, and that gives you a good start at getting something which can genuinely go down, to 20 hertz. But what you don't see is that we've got some quite clever acoustic technology in the cabinet. We use a material called ACE, which is activated carbon. It acoustically makes the internal volume look a bit bigger.
Oh yeah, I read about that. It was something about how it's like activated charcoal essentially, with a bunch of tiny little holes that when you add up the volume of all the tiny little holes, it's actually some substantial amount of air. That's
right. And when you look at it, from an acoustic point of view, it makes the volume look substantially bigger when you put this into the cabinet. It's quite an interesting technology. It has its challenges, but I don't know if there are many other loudspeakers out there that closed box and in a closed box configuration genuinely go down as low as they do. So that's the first thing that makes them unique. The other thing is it was kind of one of our first forays into looking at complex cabinet shapes. The shape of the cabinet, particularly around the mid-range driver, particularly around the tweeter, has quite a big effect on the directivity, on how smooth the frequency response is. And so we were very pleased to work with a designer like Ross, where he is interested in these kind of organic flowing shapes, because that really suits the acoustic requirements as well.
Very good. Returning to tweeters for a moment, Adam A. in the chat room has a question. We were talking about the UniQ, which has the tweeter at the center of the mid-range or mid-bass. And I guess it's a dome tweeter, is that correct?
Yes, it is a dome. And it's actually turns out to be very important exactly what the shape is. I mean, as I mentioned at the beginning, 1988 was when the UniQ first was invented, if you like. And the theory of the advantages of single point source and matched directivity were known from the start, but the details of exactly how to get the practical thing to work really well has taken us a long time, and a lot of investment in research to really figure out. And in fact, it's a kind of good timing, because the Austin was the first UniQ that we developed where we could really get the tweeter to go up as high as we liked. So that, the Austin goes up above 30 kilohertz, for example, on the tweeter, and keeps the dispersion very well controlled, nice smooth frequency response. And
Adam's,
that was...
sorry, go ahead.
I was going to say that the reason it can do that came down to some work that my colleague Mark Dodd did on looking exactly at the shape that the dome needed to be. And he came up with some very, in the end, you think, oh, of course you have to do it like that. But he came up with some very clear design rules of you have to use a dome, you have to then have a waveguide next to the dome that's exactly the right shape. And if you don't have those things, it doesn't really work well enough. So we use that on all our products now.
Adam A. was asking about ribbon tweeters. Has KEF ever worked with ribbon tweeters? And what would you say are the comparative advantages and disadvantages to the dome that has been developed here?
So I'm thinking of all the products. We have actually a nice little museum in Maidstone in the UK with our old products. I don't believe we've ever used a ribbon in KEF, but our sister company Celestion used them at one point in its history. At the moment, with our focus, our technology focus is very much on controlling the directivity, matching the directivity up between drive units. So that's where the UniQ comes from. The directivity of a driver is pretty much defined by, firstly, the diaphragm, what shape it is, what size it is, and then secondly, if you have any waveguide around it. And the difficulty if you have a ribbon is that they tend to be narrow in one aspect and very tall in the other. So they normally have a property where they're quite narrow directivity vertically, but quite wide horizontally. So from our philosophy of trying to match up the dispersion of the mid unit with the tweeter, it would be very difficult to see how we would achieve that
with a ribbon. Yeah,
with a ribbon. So that's pretty much why it's not a technology that KEF have looked into.
Creamy Corncob flying out mentioned something about the Muons being $225,000. I mean, those are concept pieces. They're not actual products that one could buy, right?
No, you can buy them. You can buy them.
Oh, okay.
So that retail price is, I'm not sure if it's exactly right, but it's in that region.
Okay.
They're a limited edition. So part of the appeal of the product is its kind of monolithic sculptural design. So it's almost kind of equal parts speaker, equal parts art installation. And then they're made as one-off pieces. So
right.
They're quite substantial things, and they're quite stunning things, and the owners of them have bought them as almost as a sculptural thing, as a design statement, as anything else.
Right. You're not going to hide those away. Your spouse your spouse had better really like them too, or else you're in big trouble. What about the material of the Unique tweeter? Jazz Blade is asking, silk dome?
No, we in the early days of Unique we used soft domes, but we used hard dome tweeters, and we have done really for about nearly coming on to 20 years now. Again, part of our philosophy is that we believe that all the drivers should move rigidly without bending in the bandwidth we're using them, and a little bit extra so we can cross them over easily. And the reason we have that philosophy is because as soon as something begins to bend, then you always see some disturbance in either the frequency response or the directivity. And our goal is to try and make something that's very smooth in terms of its frequency response, and then also when you move off axis, it remains smooth. It maybe just becomes the treble just drops off a little bit as you move off, and it's very hard to achieve that if you're using a soft material which breaks up. The other side to it is that if you don't have any bending in the material, then you can't hear the material, so you don't get the characteristic. And
that's a good point. Yeah.
We use exclusively titanium and aluminium tweeters in I think it's all of our products, from the right at the top all the way down to the bottom.
Well, we got a lot more to talk about, and we will get to that in a moment. But first, I'd like to thank one of two sponsors for this show, which is Epson. Epson's revolutionary EcoTank line of printers for home and office introduce a new age in printing. The new EcoTank ET4550 wireless all-in-one printer doesn't use ink cartridges. Instead, it features an innovative refillable ink tank. It comes with enough ink to print up to 8,500 pages, equivalent to about 50 ink cartridge sets. You're loaded and ready to print for up to 2 years. Powered by Epson's leading-edge precision core technology, it delivers high-speed, vivid colors, and laser-quality black text, plus auto two-sided printing, a 30-page auto document feeder, and easy wireless printing from tablets and smartphones. All EcoTank printers deliver an unbeatable combination of convenience and value with ultra-low-cost replacement ink bottles. Now you have the freedom to print without running out of ink. Visit Epson.com/EcoTank today to transform the way your office, home, or work group prints. For the best combination of ease and value, turn to the new Epson EcoTank printers. That's epson.com/EcoTank. And we thank Epson very much for their support of Home Theater Geeks. Epson, exceed your vision. So I'm talking with Jack Ockley-Brown, the head of acoustics at KEF, and I wanted to make sure we spent some time on the Blade, another speaker that started out as a concept speaker, but now, and like the Muon, it Muon's available on custom order. I think the Blade may be somewhat more available. Is that a retail product, or is that still a custom order thing?
No, the Blade is a retail product in 2 finishes, in black and white. But we do custom versions in various other colors, which are built to order.
We have a picture of the Blade 2, which is, I think, the smaller one. Is that correct?
Yes, that's correct, yeah.
So here it is, and I'd love for you to tell us what's special about this one. I mean, obviously the shape of it, again, like the Muon is. Yeah. You've never seen it. Well, you just don't see speakers like that.
Well, that's kind of the reason that we made it a concept to start off with. It quite nicely follows on from what we were just talking about, which is the Muon. And I was kind of talking about some of the technology we developed in the UniQ of the Muon, and that was kind of in my early days at KEF, around 2006, 2007. We were pretty pleased with what we'd done on that UniQ in terms of the tweeter. And when we launched the product, we pretty much in engineering decided we'd carry on developing that unit, trying to eliminate other, problems that we could find in it, and just, try and push it as far as we could. And we focused really on the mid-range at that point. I said earlier, the reason we use metal domes is because we're trying to get rigid drivers that don't bend in their working range. And on the original Muon, we had a plastic cone mid-range. So we wanted to design a mid-range that was totally rigid. And we kind of worked away on this. And as well as doing this work on the UniQ, we started thinking about the system as a whole thing and saying, well, we're trying to achieve this single source of sound on the tweeter and on the mid-range, but what about the bass? Is it right to then put that in a system where we put drivers, just below it, like a conventional system? Is there a better way? And the Blade layout was what we came up with. So the whole idea of that layout is to extend this idea of a single source of sound, from way up in the treble through to the mid, all the way to the bass. So if you look at the layout, I don't know if you can pull up.
We can pull that picture up again, I'm sure. Same one. We'll see that in a second, I am sure. There it is. What
we came up with was this configuration where you place the UniQ on the front of the cabinet, and then in order to get the bass drivers as close to it and symmetrically surrounding it as possibly, we put the 4 bass drivers on the sides of the cabinet. So if you kind of look at that system, you've got a tweeter, and then directly surrounding it, you've got the mid-range, and then directly surrounding the mid-range, you've got the bass. So, when we use those bass drivers, they're all fed with the same signal, and we only use them up to, a frequency where they all sum up into a single source of sound. So the bass, appears to come from a point in space that's just behind the UniQ. So, yeah, it's kind of a system where we're totally focusing on one idea. I mean, it ends up looking quite a strange thing, but for me, the thing that's really nice about it is that it's all got kind of good engineering reasons for the way it looks. So there are some spin-off benefits of this besides the single apparent source, which is once you've put the bass drivers on the sides, you're really free to make the front of the cabinet any shape you want, to make the acoustics really optimal for that UniQ driver. And it's maybe hard to see in the pictures here, but when you see one of these in the flesh, what you'll notice, or I'll kind of say to you now, have a look at this, is if you run your finger from the mid-range cone onto the black area surrounding it, and then onto the cabinet, which is white in this case, it's a totally smooth surface. There's nothing there that's going to disturb the radiation from the tweeter.
I was going to say, in terms of diffraction, very often, rectangular type speaker cabinets, have this problem of sound waves diffracting off of the edges of the speaker, but you don't have that problem here. There are no edges.
No, it's exactly right. That's a almost ideal situation. In fact, it's one of the only times I've encountered where you measure the driver in the cabinet and it measures better than when you measure it on a test baffle, because the cabinet is absolutely designed to work with that driver. The other nice benefit you get is that once you've put these drivers on the sides, they fall into these opposing pairs. And in the cutaway on the right-hand side there, you can probably just about see that the magnets of the bass drivers are actually attached together inside the cabinet.
Actually, I have a picture called Cabinet Vibrations that I think we'll be able to see. So here's a comparison of a more conventional speaker design with multiple drivers on a front face on the left, and then the Blade on the right. So tell us what we're looking at here.
This is, I kind of would say you caption this as an artist's impression.
Yeah, it's exaggerated. I'll agree.
So on the left-hand side, what we're trying to show there is that the majority of vibration of the cabinet is directly from the drivers. The driver's got a big, powerful motor in there that's having to push on the cone to make it move. And at low frequencies, it's having to push a lot to get that cone to move. And you remember Newton's third law, is it? Every action has an opposite reaction. So as much as you're pushing, as much as we're pushing on the cone, there's also the same force pushing on the motor, which then gets transferred through the chassis, and ultimately it normally ends up shaking the cabinet. And the problem with the cabinet is that it's got very big panels, and they're very big area, and they have resonances. And when they resonate, they're actually very effective at radiating sound. And what you find is if you look at the vibration of a cabinet wall, you'll find some frequencies where it's moving enough to generate a lot of sound. And it's a really horrible kind of sound because it's just very resonant and it's a very particular frequency. So, having spent a lot of time working on the drivers, we really don't want you to hear the cabinet. So in the Blade configuration...
that gives us this dual opposed thing that you were talking about.
Yeah, that's right. So if you kind of picture how the motors are pushing on the cone, they're pushing the cones both out of the cabinet at the same time. So that means the reaction force is coming both into the cabinet. So those reaction forces are pushing against each other on the opposing side. So you cancel the majority of that vibration excitation before it gets to the cabinet. And it's worth around about 20 to 30 dB of vibration reduction.
Wow.
To put that in context, that's something like the equivalent of 100 times. 20 dB is, you'd need to make the cabinet 100 times heavier or 100 times stiffer, which you just can't do. I mean, 100 times heavier, nobody could manage to make that on this. So
nobody would want to deliver those speakers to your house, that's for sure.
That's right. Yeah. And we certainly wouldn't want them back for service. But
yeah, right. Yeah, exactly.
So exactly. It's just a really elegant way to solve this vibration issue. So that arrangement's got a lot of things going for it. However, it's very radical. And so when we came up with it, was around about 2008, 2009, we had a prototype really ready to go. But we were very nervous about making a product because, it's just so different. Would the market accept it? Could, people understand these concepts? So again, similar to what we did with the Muon on the Austin, we took our prototypes to a hi-fi show. And it's a strange thing. And we've kind of ended up doing it twice, partly because of circumstance, but also partly because why not? Because you see this happening in other industries. So you'll see, particularly in the car industry, that you will go to a show and you'll see things that are just concepts. Just, hey, we might be doing this in the future. What do you think of it? And it's been really, I think, a very successful strategy for us. And, probably without doing that, we might not have been brave enough to bring a product like that to the market. But when we showed it and we took it to Munich at the high-end show there, and Scott, I think you probably saw it at CES.
I did. In 2006, 7?
I think it's a bit later, probably 2009.
Nine. You're right. I did. And you were over at the Hilton, and I came into the room, and I sat down. I listened to him for a while. Yeah.
So we had such a good reaction from the concept that we decided, let's try and change this from being a one-off pair of prototypes to, a real thing that we can offer for sale. And that's what we did. And we launched the real product in 2011. And it's it's been really a very successful product for us.
Mm-hmm. F-Loop in the chat room is asking about voicing. How do you go about determining the quote-unquote target sound? And why is it so significantly different, according to F-Loop, from the classic 80s and 90s KEF speaker sound?
That's a tricky question. I mean, we're kind of, our approach is I guess if you did a survey of the industry, you'd find us on the more kind of engineering and technical side. We try and do as much as we can by prediction, by simulation, by trying to understand what's happening. But ultimately, you have this stage at the end where you have what you've designed, and you're listening to it, and you have to make some decision based on what you can actually hear, and that's a pretty tricky process.
And somewhat subjective, obviously. I mean, you know, what somebody thinks is a great sound, somebody else might not. Yeah,
it is totally subjective, and to an extent, you have made some decisions already in the design process that will affect, you know, what you can do at that stage and what you can achieve. So you've already developed your drivers, for example. So I think one of our fairly big changes that we decided, was firstly to go for metal dome tweeters, to go for rigid piston operation, to try and get very wide dispersion. And we're doing this based on our understanding of psychoacoustics to an extent, and what we believe is the right way to do it. And that kind of determines then what you end up with in the listening room when you're trying to balance it. So I think if you compare 80s KEF, which used plastic cones, that used soft domes and didn't have Unicube, a lot of the changing character comes from us developing new technology. And I would describe it's not a voicing things per se, but just a change in technology. I think it's inherent with that if you look at the performance of those drivers, the old ones, they were designed to break up in their bandwidth, in a benign way as much as we could. And then the new ones are designed to be rigid in their bandwidth. And once we moved to Unicue, we focused a lot on getting a very consistent dispersion, which we weren't able to before Unicue, and so these decisions do determine a lot of the character of the sound. So it's not just a voice, saying we're changing our philosophy on voicing. It's kind of our technical direction determines to quite a large extent the sound of our product. Mm-hmm. So I guess the KEF sound back in 80s was always kind of known as a kind of soft sound, not without detail, but on the warm side, I would say, and something that you could listen to for hours and hours, but perhaps not the most exciting thing you've ever heard, if I was being I hesitate to be critical. No, I understand. That's an aspect we're keen to maintain some of those aspects. So we want something which isn't fatiguing, that you can listen to for a long time. But with that, we want to try and get, some progress. So, our technology that we've developed is kind of focused on trying to make things sound very natural, so that when there is bite in a recording, you can hear it. But when there isn't bite, it's not there. And, has more dynamics, because, I think we do have more dynamics available now in, well-produced modern recordings than we probably did in the past. So, in a roundabout way, I hope that answers the question. Well, it does, and thank you very much for that. We've got a lot more to talk about, but before we get to it, I do want to thank our second sponsor for this episode, which is Drobo. We're very excited to welcome Drobo back to our network, and they're a sponsor of this episode. Digital data, as you know, is essential to our lives. Drobo is the safe, simple, and expandable solution for all of your storage needs. Drobo offers a family of external storage arrays. You can either add your own drives or order them preloaded with storage. I have a Drobo 5N here that I'm just starting to set up for use with a Sonos system in the house. And the setup could not have been easier.
It's a nice black box, beautiful cover across the drive bays. You simply pull that off, slip the drives into the bays, very simple. Plug it into your Ethernet router or a switch. I'm using it on a switch, and download some software from Drobo, and boom, you've got a dashboard to control the machine. And this thing came up immediately. It was working fine. Everything was okay. Boom, done. That took me all of maybe under an hour, I'd say. So and that was with unpacking it and doing all this stuff. So it's really a beautiful thing. I had no trouble whatsoever. Next step will be to load up my iTunes library and then set up the Sonos system. I'll be reporting on that in the episodes to come. Now, photographers should also check out the Drobo Mini and the Drobo 5D. The Mini is lightweight and portable, just over 2 pounds. It has 4 2.5-inch drive bays and a maximum capacity of 8 terabytes. The 5D is a desktop unit with space for 5 3.5-inch drives and a maximum capacity of 64 terabytes. That should be enough for a while. Both have an optional mSATA SSD acceleration bay, which accelerates small file reads. This is especially useful with image library software like Adobe Lightroom or Apple Photos, as well as both its predecessors, Aperture and iPhoto. The Drobo was originally developed with the needs of professional photographers in mind, but they're also great if you work with video, want to set up your own network media or file server, which is what I'm doing, or you just want a big bucket of storage to back up your files. Drobos are reliable. Data received by your Drobo and not yet written to disk is protected if there's a sudden power loss. Man, that's cool. Even better, Drobos have an internal eUSB device where data is copied if there's a power failure to protect against long outages. They're expandable. You can add or replace drives in your Drobo with ease. No tools required. I can attest to that. They're also simple. The colored lights on the front of the Drobo communicate their status. And they're fast. They support Thunderbolt, Gigabit Ethernet, and USB 3.0 connections, although the connections vary per model, so you want to be careful about that if you need to use one or another. Visit drobo.com/twit to learn more and check out their complete line of products. And when you use the code TWIT100, you'll save $100 off the purchase of a Drobo Mini, Drobo 4-Bay, or Drobo 5N. That's drobo.com/twit and use the code TWIT100. And we thank Drobo very much for their support of Home Theater Geeks. So one picture I wanted to show here, Jack, before we move on, is this diagram of the single apparent source, which is kind of the whole idea behind the Blade. And if we take a look at this, we can see here's a sort of a schematic of the drivers in the Blade and how, in fact, they make a single point, not quite a point source, but close to a point source of all frequencies from highs down to bass.
Yep. That I mean, similar to the vibration picture we saw, this is kind of a artist's impression, but
exactly. Yeah.
I kind of mentioned this right back at the beginning. The directivity of a driver depends on its size, and at low frequencies, the driver, even if it's a big, in the case of a Blade 9-inch driver, the wavelength of say 340 hertz, because it's nice and easy. The wavelength at 340 hertz is 1 meter, so it's much bigger than the driver. So it actually radiates pretty much omnidirectionally. So you kind of have this perception in our heads that the driver's pushing air forwards and you want that to be pushed towards the listener. But actually, if you're just using that driver at low frequencies, you don't have to face it towards the listener. And we kind of know that anyway because of, we do it all the time with subwoofers. But the thing about this is, finding actually if you pack the drivers in this way and you put them close together, you can get them, even up to a point where you can cross them over to the UniQ. You can get them to look like a single source of sound.
What about the idea? I often recommend to people, if you're going to want to reproduce the entire frequency range, which of course we all do, it's generally better to the point of origin of low frequencies in a room, and now we're going to start talking a little bit about room acoustics. The point of origin of low frequencies within a room, the best one, I should say, is often different than the best point of origin of the mids and the highs, which means that a single speaker that is completely full range, like the Muons were intended to be, might not give you the best, at least bass performance within a room. Do you agree with that?
I would, but what I would say is that if you look at it from that aspect of saying, well, how do I maximize the bass performance, then that's the conclusion you'd come to. But in designing a system where you have some modest speakers and then a subwoofer somewhere else, you make life difficult for yourself at the crossover point. So you've always got to make that transition from the subwoofer, being at whatever the optimum is for the bass, and you've got the stereo speakers being at the optimum for the mid and the high. It makes the transition point very, very difficult. You're
right.
We, for example, even avoid, we generally try to use three-way loudspeakers. That's our kind of optimum. We two-way, it's quite hard to get full range performance. You're asking a lot from the mid bass driver. Three-way, you can just about do the full range. As you add it more complication, it gets much, much more difficult to get everything to hang together convincingly and get all the drivers to integrate, even within a cabinet. So, splitting it up at, say, 150 or 120 and putting, the bass somewhere else in the room makes the transition really difficult. Yeah.
It's a trade-off.
It's a trade-off, and that's kind of what loudspeaker designing is. It's trying to minimize the compromises.
Yeah. The art of speaker design. There is a science to it, and we've been talking a lot about the science, but there's also an art, I'm sure.
Yeah. That's true. And in a way, you've got to try things, to see where the limits are to an extent. There's only so much you can do by, theory or prediction on the computer.
Right. Well, moving away from these really exotic speakers, obviously KEF makes a bunch of speakers that are sort of more traditional. We wanted to touch upon the Refprint Series speakers, and we have a photo actually of the Refprint with it's called Cabinet Refprint.
Oh yeah.
So tell us how you're approaching the design of a more conventional rectilinear cabinet-based speaker here.
This is the Refprint Series is a range that we've had in KEF's portfolio for a long time now, and we've just launched a new version last year. And coming after Blade, you might say, well, why are we still making a traditional kind of loudspeaker? And the answer is because people want that. There's a big market for something which is more of a traditional looking product and not quite as avant-garde, if you like, as Blade and Muon. So that's a challenge. For the engineering team here in the UK, the question is, well, how do we get close to the performance of Blade, but with this restriction? And it took a lot of engineering effort to do it. So, I mean, if we go through kind of some of the things I've talked about, the vibration cancelling, once you have the drivers in the front of the cabinet, like they are on this, which is a Refprint 3, you have to find another way to control the vibration. And what you can see in this photo is the bracing inside the cabinet. And we have quite a unique configuration. What you can see there is that the LF drive, the bass drivers, the magnets of them touch this vertical brace which runs almost the entire length of the cabinet. And the reason we do that is we can do a lot of analysis of the vibration, and what you find is the point where the vibration is transferred into the baffle is normally the weakest point in the cabinet. The baffle rim, it's got this big cutout where the driver sits, so it's actually quite weak. So it tends to bend quite easily, and then as soon as that starts bending, other things start bending in sympathy. By rigidly attaching it to the brace, we can short circuit that transmission path, if you like, and get it straight into the main structure. The other thing which isn't that clear is we don't rigidly attach our bracing to the walls. We attach it to the walls with a damping material, which we've been through several, different materials to find an optimum. And the reason for that is, if we kind of go back to what I was saying earlier, the problem with cabinet vibration happens at resonances. If you look at either
certain
side,
frequencies.
certain frequencies, the panels move enough to make sound that's going to be, audible or just below, the level of the driver sound.
But it's going to distort what we hear.
Yeah, but it's only at these distinct resonances. So you can, in a big cabinet like that, what are you going to do about that? Can you move the resonances up above 20 kilohertz? You've got no chance because it's such a big structure. I mean, if you think, a 1 inch dome tweeter in aluminium, if you make a really, really good job of it, you can get the resonance up to maybe 40, 42 kilohertz, something like that. Have you got a chance of getting all the panel resonances above 20 kilohertz? No chance, none. So you have to have a different approach, and ours is to try and damp them. So by damping them, you try and dissipate the energy from the resonances as quickly as possible. And you effectively bring down the amplitude of the resonances so they become less audible. So in the reference, we've really focused on getting as much damping into the panels as possible. And this configuration with the bracing not being totally rigidly attached, but being damped onto the panels is the most effective way we've come up with of doing that.
It's almost like the braces have a surround.
Yes, yeah. I mean, it took a lot of research work, as you can imagine, to figure all this out and come up with a way of doing it. But it's quite a substantial benefit. It's actually a technology we first introduced on LS50, which is much more compact, less costly loudspeaker.
Actually, we have a picture of the cabinet of the LS50 as well. I thought, since you mentioned it, let's take a look at that real quick. This is a kind of a wire mesh diagram. Yeah. So you can see there, directly the driver's missing in this picture, but you can see directly behind the driver you have a vertical and a horizontal brace crossing over, and the driver meets those. They sit straight on that, and then that vertical and horizontal brace has got, it's kind of floating there on damping material, between it and the cabinet walls. Now, when I say floating, it's jammed in pretty hard, but not floating exactly. Okay,
not floating exactly, but it's a really effective way of getting damping onto those panels. So
go ahead.
Going back for a second to reference, that we just touched on one aspect there, which is the cabinet vibration, and of course, a big part of the Blade design is this single apparent source, and it's hard to get exactly that once you've gone to a conventional cabinet and put the drivers on the front, but we do still try and keep a symmetrical array. So you'll notice that we have a driver above and a driver below the UniQ. So at least we're not shifting the source of the sound down the cabinet. We're trying to keep it at the same height as the UniQ.
So those woofers on above and below the UniQ they're doing the same thing? They're not they're reproducing the same frequency range?
They're reproducing exactly the same signal. Yeah.
Okay.
So it's a pure three-way loudspeaker.
What about the ports? Your colleague Dippin sent me a couple of pictures of port diagrams.
Yes.
So I wanted to, again, artist rendering. I wanted to quickly just take a look at those. First, we have the port conventional, which you can see a lot of turbulence. These red lines are, I guess, air passing through the port, which is cylindrical in this case. Whereas the other diagram called port elliptical shows something different. So how are we? And that looks very smooth and non-turbulent. So what are we looking at here?
We're looking at an artist impression here, but we do flow simulations when we design the ports. As I kind of mentioned, we're a technology company. We're really trying to understand everything that's happening in an engineering sense. And one of the issues you can have with a ported loudspeaker is that when you play deep bass or when you turn it up loud, the flow in the port gets quick enough that you start to get turbulent effects. And as soon as you have turbulence, then by its very nature, it generates noise. So you really want to try and keep the flow as laminar as possible. And
that word laminar, explain that word laminar. Just
so laminar is a term used in fluid dynamics, in studies of fluid flow. And what that means is that you've got lots of parallel flow lines. If you look at the air passing through something or over an object, then all of the lines of flow are all nice and parallel. They're all going in the same direction.
As they are here in this, yeah.
Yeah, and that's the typical kind of airflow you will have at low frequencies, at low speeds in general. So with the port, the trick is to try and keep it doing that to high speeds. And the way you do that is to avoid sudden changes in the flow path. So the reason that the kind of first image you showed doesn't work very well is because you've got an abrupt change. The air that's coming out of the port is suddenly in open space, and the flow pressure is suddenly much lower next to the edge, and the air rushes round to the side, and that creates these vortices, and that is turbulence. It's these vortices, and that's what creates the kind of white rush, the white noise, the rushing noise that you'll be familiar with from a windy day. So by flaring the ends of the port and trying to optimize those flares, you slowly decelerate the air coming out by allowing it to have a bigger flow area, and that way you avoid these sudden changes, and you can offset the start of turbulence by quite a few dB. So it has kind of two effects. Firstly, you don't hear the noise, which is an important effect.
Oh yeah.
The other effect is that the port's more effective at high levels. So once you get turbulence, the port really starts to close up and not operate efficiently, and that then puts more strain on the LF drivers, and it really restricts the amount of bass you can get out of a port. So it's really a win-win to try and keep the flow in the port as laminar as possible.
Creamy Corncob in the chat room is asking, what material are you using for damping? And I guess, Creamy Corncob, you might mean that that material that they're using to decouple the bracing from the sidewalls, or perhaps damping material inside. Do you use damping material, Jack, inside the cabinet, as many speaker makers do?
Yes, we do. I mean, to answer the first question, the damping material we use on the cabinet construction is totally focused on controlling vibration. It's a material which took us a long time to find. So as you can imagine, we keep that as
you're not. Yeah. I don't mean to disclose any company secrets or anything here.
But it's also important to use damping in the enclosure to control acoustic standing waves. So I think your listeners probably are fairly familiar with that phenomenon, where you get a sound wave which bounces off parallel walls and continues to reinforce itself until you get an acoustic resonance set up, and you get this standing wave pattern. So this is a problem you have in rooms. You get room modes where you'll find all the basses in the corners and none where you're listening, which is the typical problem. It also happens in enclosures and in ports as well, and in any enclosed acoustic space.
Sure.
So we do use acoustic wadding, we'd call it, to try and control that. But it's kind of a double-edged sword. If you put a lot of acoustic wadding in, especially a ported cabinet, you can really kill the bass. You start to absorb energy that would otherwise couple into the port and radiate useful sound. So our approach is to try and design the layout of the cabinet so that we don't have to use too much damping. So it's
certainly
kind of similar.
Pardon me for
kind of similar to moving your speakers around in your listening room until you get the best possible sound you can in your listening position. You can think of it as we're doing the same thing. We're moving the drive around in the cabinet until we're getting the best possible response. Then we're putting in the minimum amount of acoustic wadding to control the standing waves that are left.
I just had an image of filling my home theater full of acoustic wadding. That wouldn't work out too good.
in the UK with our cold winters, that might be a really good idea.
That might be good, yeah. And the one point I was going to make was that the standing waves within the cabinet, I'm pretty sure, are generally speaking more problematic with these rectilinear cabinets than they are with these curvy shapes like the Blade and the Muon, right?
Actually, not particularly.
Really?
You get yeah, it's interesting. I'm sure this will be something that a lot of your listeners go, no, surely that's not right. But if you're interested, there's a white paper we have on our website where you can look at some standing waves that you get in cabinets with non-parallel walls. You get standing waves in any cabinet. It's just very easy to visualize what goes on when you've got parallel walls. And the thing that does happen when you get parallel walls is that all the standing waves are harmonics of each other. So, you could say, well, maybe, because, instruments also will have, a harmonic series when they play, maybe standing waves that are harmonics, you could say, well, maybe psychoacoustically that's worse. But in terms of their severity, it doesn't really affect them. What does affect them a lot more is exactly where you put the driver. It's the same as saying, well, if you put a subwoofer in the corner of the room, you always get, all the standing waves excited. And it's the same in a loudspeaker. If you have the driver right up at the end of a cabinet, that's the worst possible thing you can do. So, but again, we talked about compromises before. The challenge is to try and come up with a whole system where you're avoiding putting the drivers towards the ends of the enclosure, but you're still getting a good, position on the outside of the cabinet so they all sum up nicely. And you continually find these things in loudspeaker design where you have things pulling you in opposite directions, and you have to try and find a compromise.
It's always something, isn't it?
It is always something. So, I mean, in terms of that particular one with the rectilinear, in a three-way system, you're using the bass section in a limited frequency range, so you don't need to introduce if you get the drivers in a good place, you get the ports in the right place, you don't need to introduce too much wadding to control what's left of the standing waves.
I see your analogy, and it's a really good one. I'm going to use it myself, if you don't mind, about where you place the drivers in the cabinet is akin to where you place the speakers in a room. Yeah, that will have a big effect on the overall sound. That's really, really cool.
And the port as well is the other thing.
Yeah.
So, I mean, the port is just this open aperture that, it helps you at bass. It produces, a lot of extra output, but potentially it's a big hole that mid-range can come through, and very colored mid-range, because it'll be all of, the sound of these standing waves. So if you put your port in the corner, again, you'll couple it into all the standing waves, and you're much more likely to get them radiated through. And so we optimize the port positions as well. And, in fact, one of the common questions we get is, well, why do you always put the ports on the back? But it's kind of a case of, well, every little bit helps. If you put it on the back, then anything that does escape in the mid-range is shielded from the listener by the cabinet. And that's a big effect. That's worth, kind of 4 or 5 dB of attenuation of these mid-range.
Wow, I hadn't thought of that.
So, yeah, we kind of look at these things in quite a lot of detail. And because there's so many compromises, what you tend to do is try and find a few things to help you out and stack up the effects. So you get, kind of a couple of dB here, 4 or 5 dB here, another 3 there, and suddenly you've got a 12 dB improvement, and that's a big performance improvement overall.
Yeah, no kidding. Well, listen, we've come to the end of a fascinating hour, and I want to thank you so much for being here, especially from London, where it is rather late at night. Thank you so much for staying up.
You're very welcome, Scott. I've really enjoyed it. It's been a pleasure, and I apologize for my somewhat dodgy internet connection.
Well, we did find a solution to it, so I think we're good. Thank you so much. That's Jack Ockley-Brown, the head of acoustics at KEF in London, and we thank you very much.
Thanks, Scott. Thank you.
Okay, you can find out much more about KEF products, obviously, at KEF.com. You can find me at avsforum.com. You can email me at scott@twit.tv. And you can follow me on Twitter at htgeekscott and at avsforum. You can always find previous episodes of Home Theater Geeks right here at twit.tv/HTG and on our YouTube channel, youtube.com/twit-home-theater-geeks. Next week, my guest geek is scheduled to be Barb Gonzalez, otherwise known as the Simple Tech Guru. We'll be talking about the latest in streaming, and there's a lot to talk about, she tells me. So I do hope you will join us. Until then, geek out.